So today we're looking at the heat engine. This is a continuation from what we had last time. In the previous lesson, we were talking about the first law of thermodynamics, applying the non-flow energy equation. So this time around, we would want to apply this now on how heat is utilized in an engine with the application of the first law, where we consider that the total heat energy actually gives us the work done. And then we'll see how that works out. So first of all, before we even proceed, we need to do work out some definitions. So what is a heat engine? In this case, we're defining a heat engine as a system that normally operates in a complete cycle. But one thing is clear in this definition, that it is supposed to do work from a source of heat. Now, when we compare it with the second law implies that this heat engine operates between a higher source of heat and a sink. So meaning that it receives the heat and it dumps it to a sink, but in between the two, it's able to do work. So that is what a heat engine comprises. Now, in engineering, we normally enjoy looking at a problem like this or analyzing such a question or such a scenario using a diagram. So look at this. How does work come about when we consider heat? How is this engine able to do work? So look at this diagram here. So the first thing you can see is that we have a high temperature or hot reservoir. Heat moves from this source where it is in high concentration, coming to the engine. Now what happens in the engine is that we are going to have two movements. The first part is that this heat engine is going to do work. And at the same time, the remaining amount of heat will be rejected to a low temperature or cold reservoir, which is a heat sink. In every other given engine, this is normally taken care of by the cooling system, which normally takes up the heat from the system, which would have remained after work has been done. So this is a diagrammatic presentation of a heat engine and how the system goes around. So now, if we want to find the net work done, it means that we have to subtract the two values, the gross heat or the heat that came from the source minus the heat that has been dumped into the reservoir, or rather the cold reservoir or the sink. So that's why the formula there is saying work, or simply net work, is the difference between Q1 and Q2. That's how this works out. Now, let's look at an application. We're going to look at an example that will apply this principle. So we have two examples. Here is the first example. Yeah, this can hide. So the first example says that heat is transferred to a heat engine from a furnace at a rate of 80 megawatts. If the rate of waste heat rejection to a nearby river is 85 megawatts, determine the net work done and the thermal efficiency for this heat engine. All right. So as usual, let's start with the data. What information do we have? First of all, we've been given that the heat coming from the furnace, the heat from the source, which is Q1, 80 megawatts. Q2, this is now the heat that is being rejected, the heat that is coming from the system, the heat coming from the engine is 35. And one thing you realize is that this number, Q1, must always be bigger than Q2 for a normal engine, unless we talk about a different system. But for a normal heat engine, that's how it's supposed to be. The source should be higher, should have a higher amount of heat. So Q1 80, Q2 35. Now, how do we find the net work done? Remember, the question is asking us to find, first of all, the net work that has been done. And also then after that, we get to the thermal efficiency. So the formula, we say that if you want to find the net work done, then you just have to subtract the gross heat coming from the source, take away what has been dumped into the heat sink. Q1 minus Q2. The heat from the source minus the heat that has been rejected from the system, that gives us the net, the heat that remains to do work. Now, this is the heat. If you're considering the engines that we use in automotive engineering and heavy equipment, you realize that this is the work, the kind of work that is going to be used to run your engine, perhaps to crank your engine and spin it at the needed speed. That heat that has remained there. So now that we have this formula, all we are going to do is replace for Q1 and Q2, and that's it. Find the net work done. So there we are. So we're saying 80 take away 35. Now 80 minus 35, the answer is therefore 45 megawatts. That is the network done. Let me go through this again. We are saying heat is being transferred from the furnace at what rate? At this amount of rate, which is 80 megawatts. Then after the heat has come from the furnace, it is being dumped, not the same amount of heat, but what is going into the nearby river is 35 megawatts. Where has the other one gone? That is now where the question comes in, as it says, determine the net work done. So then we can now say, let's get to work. Basically, we're applying the second law, which talks about how heat moves in such a manner. Now, having done that, then we go back to the formula, which is the work done, the net work done is supposed to be the difference between the gross heat energy or the heat energy coming from the source and the heat energy that has now been dumped into the sink or cold reservoir. So this is where we can now just substitute Q1 minus Q2. If you check our data, our Q1 is actually this number here, 80. Then Q2 is 35, meaning we just go ahead and substitute. 80 take away 35, 80 minus 35, our answer is 45 megawatts. And there we are. But the question didn't just end there. It also required us to find the efficiency, in this case, the thermal efficiency of this heat engine. So the formula for thermal efficiency is where we talk about, first of all, the network divided by the heat coming from the source, everything expressed as a percentage. So the other way is where you may decide to write it in this format. To find this work, it's the difference between Q1 and Q2, then the Q1 being the source, being the denominator, everything by 100. That's how this is done. So meaning we can now just go ahead and substitute. Our network, we found it to be 45. Heat coming from the source, 80. And this is our 100. So 45 over 80 times 100, the answer is actually 56.25%. 56.25%. Quite a good number for an engine. Well, we know different systems behave differently. For us, this is the value that we have. Let me go through this again. We're saying we are looking for the thermal efficiency. To find the thermal efficiency, we take the ratio between the net work done and the heat from the source expressed as a percentage, meaning we're saying work, which is W divided by Q1 multiplied by 100%. Or if you want to do it the way we did it from where we're coming from, it's Q1 minus Q2 over Q1, meaning the heat from the source minus the heat going to the sink divided by the heat from the source. Everything expressed as a percentage, meaning you multiply that by 100. So let's get then to efficiency. This is now 45 divided by 80 from your calculator. Whatever you get there, then times 100. So the answer now comes out as 56.25. Once again, if you realize there's something that you need to clarify, you can always post on the comment section or write in the comment section, or you reach out. Sure, most of you may already have my contact. Reach out to where you need to get in touch. Let's pick up another example. Now, in this example, it says, let me just reposition this. Okay. In a steam plant, the turbine develops 1,000 kilowatts. Heat supplied to the system in the boiler, 2,800 kilojoules per kg. Heat rejected by the system to the cooling water in the condenser, 2,100 kilojoules per kg. Feed pump work required to pump the condensate back into the boiler, 5 kilowatts. Calculate the steam flow rate. Now, this information looks like lumped together and you can see some things are juggling left, right, and center. But let's go back and try to write down the data so that you can call a spade a spade. First, heat coming from the source is 2,800. The heat that is going to the cold reservoir, to the sink, is 2,100 kilojoules per kg. That's the heat that has been rejected, the heat that has come from the system after work has been done. Then power developed by the turbine. How much power has been developed? We thought the total power developed is 1,000 kilowatts. But it comes with a condition. In order for although it has developed this, there's a requirement that the pump should pump back the condensate back to the boiler. How much is it going to take? It will take 5 kilowatts. So that's how come we're saying W1 is 5 kilowatts. Then W2 is, rather W1 was 1,000. W2, which is later on like loss, is 5 kilowatts. So before we do that, we need to calculate a number of things. Let's start with the net heat supplied to the boiler. So we're going to make sure that we don't mix mangoes with apples. We allow mangoes to stand on their own and apples to crack their day. So net heat supplied to the boiler, as we did earlier, this is simply Q1 minus Q2. The heat coming from the source minus the heat that is being rejected by the system. So that's Q1 take our Q2. The next thing we can do is simply substitute. The next thing we can do is just substitute for Q1, which is 2,800. Then Q2 we substitute also for 2,100 in this format. So we're saying the net heat that has been supplied is supposed to be equal to 2,800, which is the heat coming from the source, and 2,100, subtract 2,100, the heat that has been rejected. When you subtract this from your calculator, you find the net heat. In this case, 700. This is just like we had in example 1. This is representing the work done, although it's referring to the work done per unit mass of this working substance, which is the steam. Now, we don't know at what rate it was flowing, so we'll get to that. Let me go through this again. We're saying that the heat that is in the turbine is 2,800. So we're saying that this is what has been supplied to the turbine. Then how much has it rejected? It has rejected 2,100. Can we account for the loss? What about the difference? Where has it gone? We'll get to that. And that's the one we'll say that will be like the net heat remaining in the system, equally representing the work done, because that is what has been converted to work. Then the power or the work done per second is 1,000 kilowatts. Feed pump work required per unit time, 5 kilowatts. So with all this, we'll ensure that these familiar units talk to each other. Because they are now, they're simply referring to the data on the heat side. So we can now go back to how do you find the net heat supplied to the boiler? This is where we said the net heat is given by the difference between the heat source, the heat coming from the source, and what is being rejected by the system. So hence you can see we're writing it here as Q1 minus Q2. Q1 take out Q2. So Q1, if you check the data, is 2,800. Q2, 2,100. What is the difference between them? Here you have it as 700 kilojoules per kg. This is the net heat. Like I emphasized, it's like even representing the work done per unit time or per unit mass. Now, let's finish up because the question is asking for the mass flow rate. We're done with the heat. Let's now temper with these two, the work per second or the power. Net work per unit time or simply net power output. So here we subtract power developed by the system, take away the power that is being used to pump back the condensate back to the boiler. Then we'll have the net work done per second. So here we're told that the power that was developed is 1,000, and it only took out 5 kilowatts of that power to supply, to make sure that the pump can run and pump back the condensate back to the boiler. So 1,000 take away 5, you get 995. Check your calculator. Now look at this again. This is now in kilojoules per second. This is in kilojoules per second. So now, here we are trying to emphasize that that net heat transfer is representing the work per unit time. But there is a problem. The units are not talking to each other directly. So that's where now we come in with this expression on the left. If I multiply the mass flow rate by the net heat transfer per kg, what I will have will be in kilojoules per second, because the kg will cancel out nicely. Then this is the net work done per unit time. So we remain with the two side by side. So if we want, we can make M the subject. I think we'll do it in the next stage. So here we have it. We just substitute. The heat, the net heat is 700. The mass flow rate, we don't know. The net work done per second is actually 995. So if you make mass flow rate subject to the formula, you get 995 divided by the 700 coming from the other end. So hence you have the answer here as 1.42 kgs per second. So once again, this is how you find that power. We're saying, get this one found, calculate it on its own. The difference between the power that has been supplied and the loss due to the pump. To feed the pump, to make sure that it runs, it pumps back the condensate, we are spending 5. And yet what is being developed in the boiler is 1000. So our net at this point, with the information provided, our net becomes 995 kilojoules per second. Then, since we have our net here, and we also have our net heat, so we can just now make sure that the net heat is converted to the work done per second. This is why we now multiply by this mass flow rate, such that if you multiply the mass flow rate by the heat per second, or the heat per kg, you get the power, rather the work done per second. So we now have room now to equate the two. So where there is heat, although here I just swapped them, the net heat is 700, the mass flow rate remains the mass flow rate. Then this is the network per second, the network done per second, so we have 995. So then our mass flow rate becomes 995 divided by 700. And our answer then is 1.42 kilograms per second. So for now, you also have an exercise just with 3 questions. Try them out. The answers have already been planted there. In the previous lesson, I think the exercise that I provided didn't have answers, but I will soon be correcting that. I will send them so that as you practice, you will not have to struggle. Okay, thank you very much. We'll link up in the next class.